Welcome to chapter 10. So this is our final chapter that we are going to do in the book, and it's on graph theory. Now, before we get too much into graph theory, I'll be honest, graph theory is my specialty. This is what I did my PhD on is graph theory. It's an area that I love, and we have a much deeper class in graph theory and so forth. We're just going to introduce the basics of graph theory and some graph characteristics. We've already done some basics prior to this in the class. But this is where we're going to get into some real theory and some real concepts and questions and different things that they actually answer. Now, I'm going to admit ahead of time, this is going to be a longer video because there's a lot of information to kind of cover in terms of graph theory. So first, we're going to talk about what are called trails, paths, and circuits. These sound very, very similar, and they actually are similar. However, they have different concepts. The concept, and they actually go back to the very origins of what people say is the origin of graph theory, which was something that Euler came up with when he was looking at the town of Königsberg in Prussia. And Königsberg is very, very famous because of what's called the seven bridges. So this is a picture of Königsberg on the right and then a drawing on the left. And to point something out, there are seven bridges and there is an island right here in the middle. That's where B is. And then there's also this landmass over here, and the river keeps flowing on. So yes, I know eventually you come back and it connects, but in Königsberg, you have the town is essentially broken into four areas, area A, B, and C, and there are seven bridges that connect this place. Now, the question that Euler dealt with, and it's a really good question, is it possible for a person to walk around the town, starting and ending at the same location, and cross each bridge exactly once? So in other words, if I start here, can I move around and cross every single bridge and get back to A, but I have to cross every bridge once and only once. So no bridge can be used twice and no bridge can be skipped. Now, this is the puzzle that Euler actually wanted to use graph theory on. And so what he did, I'm going to come back here, is he essentially introduced the idea of graph theory. So in graph theory, remember we have nodes. So he made a node for each of these different land masses, A, B, D, and C. And then he drew a connection for them if there was a bridge. Now, the beautiful part about graph theory is that we can technically move things around. I can take this spot right here, and I could make this vertex slide over here. And oh, did not mean to do that. And if I do that, you end up with this graph, and it can look a lot of different things. I drew it this way. You see, it's very similar. But the idea for this was, is there a way to do it? And the answer to that is actually no. And we'll get to that a little bit later. The origins of a term called Eulerian, because it's from Euler. Now, so this is what we did is we took our answer, we turned it into a graph like this. And this is the way that we can attack the same puzzle that we had here. And so he's did this and then asked questions about that, and that led to a lot of questions for graph theory. It also led to some key definitions. And I'm going to go through these definitions because these are very, very important definitions for what we're going to talk about. The first is called a walk. From vertex V to vertex W is an alternating sequence of adjacent vertices and edges. So I start with vertex, edge, and so forth. To sequence, and this vertex has to be incident to this edge and so forth. And so the vertices have to be adjacent, and then the edges from which I pass have to be this way. So again, just coming back up here, I can't go A to D because I'd have to, there's no edge between them. They're not adjacent. But I can go from A to B, and then I have to tell which of these two edges did I take. So that's the idea of a walk. And a trivial walk is a vertex from itself. We ignore it. Technically, it's out there, but we ignore that walk. Couple little things just to keep going at this point in time is that a trail is a walk that does not contain a repeated edge. So up here, I could have repeated an edge. If we say I'm not allowed to use something twice, we get into this idea of a trail where I do not have a repeated edge. And a circuit is a closed walk that contains closed walk is a walk. So it's a walk that starts and ends at the same spot. So a walk doesn't have to start and end the same spot. So closed walk does. And a circuit essentially is a closed trail. It's because you cannot have any repeated edge, has to have at least one edge, and has to come back to itself. So just real quickly to come back to this graph to illustrate, a walk, a closed walk, I could have gone A to B and then right back on the same edge. However, if I did a closed circuit, so I'm trying to, this would be a walk from A to B and D. That's not closed though, closed I have to get back. But if I go A to C to D to B and then back up on the same edge, well, I got back to A, I reused the same edge. So that's a closed walk, but it's not a circuit. To do a circuit though, I could just do A to B and then up the opposite side. So that would be a circuit. So this is where we get into this idea of circuits. And we can even things called a simple circuit, which we do not have repeated edges except for the first and last. Usually this is actually referred to as a cycle, not a simple circuit. But your text decides to go a little bit different. I will probably use the term cycle because that's actually the more common term throughout graph theory. And a path is, okay, let me put it this way. It's a walk that does not have any repeated edges or repeated vertex. So paths and cycles don't have repeated edges or vertices. And a circuit and a trail don't have repeated edges, but could have repeated vertices. And last but not least, a walk can have whatever I want. I can go anywhere. So this table, which is from your book, and you look at it, it goes through all those different things. Does it have to contain at least one edge? Truth is, most of these are no. If you have a circuit or any kind of circuit or cycle, again, the last one is really called a cycle, not a simple circuit. That is really what it's kind of goes into. Now, it says yes. Again, there's actually argument across mathematicians. Does it have to? Usually we say yes, but we ignore the cases. Usually we're not dealing with those trivial cases of that size. So let's just kind of look at an example to kind of illustrate this. So if I wrote E1, E2, E3, E4, if I just wrote these edges, E1, E2, E4, and then E3, that you can imply that I started at V1 and went to V2. And then I had to go through here, and then I had to go here, and then I had to go here, because the only way to go from V1 to V2, I mean, use edge 1 and then use edge 2 is I have to get to V2, which means I had to start at V1. So I could have written it down with those things, and that's pretty clear. However, if I just wrote the edge E1, that's problematic because there could have been two ways to do this. Further, if I do something like this, even if I do the vertices and I write them as V1, V2, V3 for the same thing. If I do a V2 to V3, I could have gone this way or I could have gone this way. And so just writing the vertices doesn't really mean a whole lot. We have to be kind of careful with these different notations that we understand. So when we allow multiple edges and loops and things like that, usually, which by the way are typically in a graph like this, which is a multi-graph. If we have a simple graph where there are no double edges, where there's only one edge between any pair of vertices, at most one edge, then we can literally just write the vertices and we're perfectly fine. Because we have multi-edges, it actually becomes important to identify the edges. That's the main thing that's messing up this one. Similarly here, the loop throws things off. Because if I just wrote V in this graph down here, I went V1, V2, V2, V3. Well, there's only way to want to do that. V1, if I'm at V2, the only way to get V2 is do the edge and then come along here. However, if I was to write something like V2, E2, V3, it could mean a couple different things in this situation. So this one's actually pretty easy because the edges are only attached and there's no double edges. So double edges are really what cause things to get messed up. Let's look at another one. Let's talk about whether or not these following things are trails, paths, circuits, or I'm gonna call this cycles. Again, I'm just gonna cross that out and call it cycles. I don't like now the only reason it's called simple circuits is because technically this is on a multigraph and a cycle is on a simple graph, but I'm gonna call them cycles anyways. Cycles. Can't spell today. So in a cycle like this, let's think about this first one. V1. So the first thing to look at is simply, do I have any repeated vertices? Yep, I got repeated vertices right here. Do I have any repeated edges? Edge, edge, edge. I have 4 edges. And then last but not least, does it go back to itself to start and end of the same spot? This one does not start and end of the same spot. So therefore, it cannot possibly be a circuit or a cycle. Further, it has repeated edges, which means it can't be a path. The only option then is it's a trail because we have no repeated edges. What about problem number B, where I have E1, E1, E3, E5, and E6. E5, E5, E6. Well, the simple fact that I have repeated edges means that it has to be it's just a walk. Repeated edges limits me to this idea of walks, whereas a trail, remember, trails do not have repeated edges, so therefore we can kind of throw that out. It doesn't end or start in the same spot, so again, we can kind of work through here. So this is the main idea that we can kind of work through this process and we can draw out on each one of these. How does it work? B is an interesting one because it actually illustrates, what if I just have the vertices? How do I get from them? And it kind of heads down this kind of random path. So we're starting at V2 and going to V3. Well, there's only one edge possible for that situation. And then from there, I'm going to V4. So I have to go this way. Then I'm going to V5, have to go this way. Then I'm going to V6, I have to go this way. And then I have to go to V2. Well, notice it began and ended at the same point, which actually makes it, and I have no edges that I use twice. I have no vertices I use twice. So it's going to be a cycle. So cycles, by the way, all cycles are circuits. That's kind of an important kind of idea, is that and the only reason we don't call cycles paths is because a cycle closes and reuses the same vertex for beginning end, whereas a path does not. But otherwise, they're pretty much the same thing. So we have a lot of these things, and there's kind of this repeated process. All right, let's move on. Talk about subgraphs. So subgraphs are part of a graph. And specifically, there's 2 kinds of subgraphs. Just in general, subgraph is I'm essentially removing any vertices or edges. And please do not say vertexes. It's vertices or edges. As long as if I remove a vertex, then I have to remove every edge that's has that as an has that it's incident to that edge. So whenever we're doing this, we have that. Now an opposite one. So this allows me then, so for instance, if I have, let me show you an example. So if I have the graph, let's do a super simple graph here. Suppose this is my graph G. Then if I simply removed one edge, like this is a subgraph of G. However, there's a fancy term we sometimes use, especially in graph theory, called an induced subgraph, which would mean that I don't remove just an edge, I remove vertices and then any incident edges. So I can't do this to do an induced subgraph, but I could have, if I deleted all of this, then this portion down here, this little triangle, would be an induced subgraph from my original matrix. And the reason induced subgraphs are actually typically studied more than just general subgraphs are because an induced subgraph is just looking at essentially zooming into one specific part of the graph and looking at it and saying, okay, well, if this is inside this part, property is inside this part of the graph, then that means what about the whole graph? And it's really, really valuable because there's a lot of graph properties that are called hereditary, which means we can kind of blow them up on different ideas. All right, so let me go through another example to kind of help you see how we can use subgraphs. So let's list all the subgraphs of a graph with a vertex set 1, 2, and edges. And here's the E1, E2, E3, where E1, well, it's only incident to V1. That means it has to be a loop. Oh, sorry, E1 is incident to V1 and V2. So that's there. E2 is only V1 and V2. So both these are between them, V1 and V2, and E3 is the loop. So it's going to give me this pretty picture right here. And if we're looking at this, all the subgraphs, there's lots of possibilities because one subgraph, just like a subset, is just to leave the graph all by itself. Okay, there's one. Now let's start talking about what are the things I could delete. I can delete E1, E2, and E3. I can delete each one individually and leave the rest. I can delete two of them. That's two, choose three. Okay. I can delete all three of them. Okay. And then we can start talking about what happens if I delete edges and vertices and which things we are keeping around. And to kind of show you, now I could not, like for instance, delete V1 and still actually even have any of these edges. All these edges have to go away if I delete V1. However, if I delete V2, I could have both V1 by itself or V1 with a loop and we're still fine. It gets to this essentially is how it breaks it down. Now this being able to break it down and look at different subgraphs, that does actually still have valuable, even though these aren't hereditary subgraphs or induced subgraphs, because this idea, because you can still overlap them and so forth, that maybe I'm just missing some information, is actually part of what is used when we actually use some different neural networks and so forth to identify what is going on when we're reading an image. We're using a tree and we're looking for maybe some of these connectedness and kind of these properties because most words are just, you can consider them graphs with some kind of loop involved in the process. Loops or lines or curves, all those wonderful parts. So we break it into smaller chunks or smaller subgraphs and go from there. All right, so that's subgraphs. The next key definition we need to talk about is called connectedness. Now, this feels fairly what it sounds like. By the way, a lot of things in graph theory describe exactly what they say. So connectedness is referring to if there is a path, a walk, any of the following from one vertex to another vertex. Usually refer this in terms of walk. We don't worry about paths, but if there's a path, then there's a walk, guaranteed. So we really are saying if I started a vertex, is there a way to get to another vertex by traversing the edges, nothing but the edges? And if so, then it is connected. And if it's connected, then for any two vertices in the graph, there's some walk. That's really, really valuable because it's an if and only if, which means if I say it's connected, then I know that every pair of vertices have a walk. If I can show that every pair of vertices has a walk, then it's connected. So the negation of this says it's not connected if there's at least some pair of vertices that don't have a walk. So let's look at some examples so you can really see this connectedness come out. Is vertex A connected? The answer is yes. Is because you can see if I have V6, I can easily traverse the edges and get over to V1 and everything in between, same way. Now, is this second one that way? And the answer is no, because obviously V4, I can't get from V4 to any other vertex. There's no edges, so V4 is stuck. The trick question is this. For C, is that connected, yes or no? I want you to think about that for a second. All right, what's your answer? The answer should be no. Here's why. Just because you see edges that look like they're overlapping doesn't mean they actually are. We could have simply redrawn them to look like this, and then it's very clear that they are not connected. So just because the lines overlap does not mean there's actually any way to go back and forth. So to speak, it's like looking down at a set of crisscrossing roads where V2 to V6 is a road and V1 to V4 is a road. Just because from above there's a crossover doesn't mean there's actually a way to get from V2 to V1 based on what we have. All right. So this is where we get a very interesting concept. If a graph is connected, then any two vertices are connected by a path. If vertices V and W are part of a circuit, remember circuit is a closed walk with no repeated edges, and one edge is removed from the circuit, there still exists a trail between the two. Because in other words, I've cut off one side of that circuit, I can still get around the other side. And if G is connected, and G contains a circuit, then the edge of the circuit can be removed without disconnecting G. So that's really, really valuable and actually gets into a component we call two connected. What's the K connected graph is a cut set is the minimum number of edges I need to remove or vertices I need to remove such the graph becomes disconnected. This is a really big thing that we actually get into is looking at how many vertices do I have to take away to make a graph no longer connected. So if H is a connected subgraph of G, well, it's connected component. Connected component really means it's a subgraph and it's connected. And then the last one is there's no connected subgraph of G has G as a subgraph and contains vertices or edges that are not in H. Meaning it's pretty much a maximal. This is partially not true. Usually when we say component, it's saying maximal, meaning we can't make it any bigger. So for instance, let's look at here. V1, V2, and V3 are all connected, but I cannot add any more edges. If I said that V5, V7, and V6, they're all connected, but they're not a component because VA is still connected to them as well. So the three different components of this graph are going to be this, and this. And by the way, we call this one the trivial component because it's just a single vertex or isolated component because it's an isolated vertex. So we do really want to know how many components we can break it up into because these are distinct groups. So if I'm looking at a network of some sort, I want to know how many components do I have because then I know I really need to operate with each of those different situations separately. So let's move into Eulerian circuits. So an Eulerian circuit, which I don't know why your book calls it Euler, they're called Eulerian. Again, your book has a lot of really good things, and there's a lot of things that it does that don't fit the rest of the graph theory community. So I really don't understand this sometimes. But going back to the original question, remember we had those different things. And our question was, could we start at the same vertex essentially, traverse every single edge, because it's every bridge, and get back to the original vertex? The answer, it turns out, is no. So as a quick reminder, let me draw our famous bridge problem again. Vertex, 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 vertex. And the question was, so Eulerian circuit would be one that is able to do. And it turns out that Königsberg is not an Eulerian circuit. So this right here, if I start here at this vertex, I have three edges to go down. If I go down this one, then at some point in time, I have to return on one of the other two. So let's say I come back in on this edge. Well, then I have to go out on this third edge. And notice if I do that, it's completely impossible to return a final time, which means the only way, if I have to use every edge in a vertex, every edge I come in has to have an edge that goes out for everything else. And the first vertex for every edge I go out has to have an edge that comes back in. In other words, it has to have an even number of edges for each vertex, or as we call that, an even degree. Further, we have to say it has to be connect, we could take it a step further and say, suppose the graph is connected, because if it's not connected, obviously it's not, there's no circuit. But that's the idea here. And this is the great theorem, is that you know if a graph is Eulerian simply by checking all the degrees. If all of the degrees happen to be even, then you have an Eulerian graph. And then we get a bunch of other properties that we can kind of work with. So again, let's apply that. Here is a wonderful little graph. I'm going to ask, is this Eulerian? And the answer to that is very simply no. And it's easy to see because you just simply look at either V3 or V1. The degrees of both V3, write that down, the degree of V3 equals the degree of V1, which both of them are 3 because they have 3 edges coming out of them. 1, 2, 3. 1, 2, 3. We're just counting here. Now, because that is, and that is odd, because this is odd, it tells us not Eulerian. Now, notice V4 and V2 are both even because they have 1, 2, 3, 4. 1, 2, 3, 4. So here we have Eulerian, but it turns out that it's not, does not satisfy this property. And that's kind of the point that we can, it's not about does every, so it is about does everything have even, or does some vertex. Again, this is how we use logic. Remember, the opposite of for all is not some. And so you got to kind of play with that when you're negating it. And again, that's the critical part about talking about these things. So further, this is the final theorem that we can kind of mention about this one, is that if a graph is connected and the degree of every vertex is an even integer, and it'll be positive, then G has an Eulerian circuit. Or G is Eulerian, as we generally say it. Let's look at this graph. This graph, it turns out, is Eulerian because we can simply go around and write all the degrees we really wanted to. And we have degree, sorry. For some reason it scooted on me. All right, so this has degree 2, degree 2, degree 2, degree 4, degree 4, 2, 4, 2, 2, and 2. All degrees are even. So therefore, it has it. Now, the way we find it is actually kind of interesting. And the way we know this whole evenness is actually based on the proof of this, which is kind of an interesting concept. So let me show you actually how we run that algorithm step by step. So what we're going to do first is we start with some vertex we'll call A, and let C be a circuit. So we just pulled a circuit. So A, this is an easy circuit that I have going on. Now I say, what's another circuit? Now it's not Eulerian because it doesn't. So I just pick a circuit. I pick a set of vertices that are all even edges. And I'm going to fuse that with another circuit. Namely, I have A, B, C, D, and then I could just roll around the outside of this thing and roll all the way back. And now I've done A, B, C, D, E, G, H, J, I, D, A. So this is the whole circuit. And notice there's a directionality. That's kind of an important thing because we're moving in a direction. Well, this is not yet Eulerian because we still haven't hit everything yet. Well, how do we get through the rest? Well, we patch into it by saying, what is not yet covered? Well, that's E. And if I start here at E and I go to H and go to F and go back to E, I'm still back here. And so if I take that, I can log that in literally where the E is. And so this E, F, H, E just jumps in with E, F, H, where there was just an E here, we expand that part out. Similarly, coming back up here, we originally had A, B, C, D, A. Well, because I had this thing right here, which was D to E to G, et cetera, all the way back to D, I just replaced the D with that circuit. So we're plugging in one circuit after circuit after circuit, essentially gluing them to pieces until we have our entire Eulerian circuit. And just like that, we have an Eulerian circuit that does everything. And it kind of lets us kind of graduate through this and see it on a whole different level. All right, so Eulerian is really, really cool because Eulerian, but notice Eulerian let us use the same vertices. We went through D a couple times, E and H a couple times. So we had that. What happens if we take on some different things? So that's going to get us into Hamiltonian. Let me hit these last couple of questions right here, these key theory, a corollary, and that a trail is Eulerian. It's not a circuit, it's just a trail. It just means it doesn't end at the same spot. So, and this is Eulerian trails are less common than circuits. Circuits are more commonly asked. But a question might be this. So suppose this house is open for public viewing. Is it possible to find a trail that starts in one room, starts in A or B, and gets to the other one without that way I can have everyone come in one room and work their way through in a specific order and get out through B. We want to know what is that trail because that's extremely valuable. Well, the way we do it is literally we change this into a graph. So instead of looking at it like this, we make each of these vertices. So next time you have a puzzle like this where you're trying to do a maze, you can literally make each open corridor a vertex. And we're going to ignore the exterior doors. If they have an interior door, we're going to make them adjacent. Now, to be Eulerian circuit, I mean, Eulerian trail is the same thing except for my beginning and my end. They don't necessarily have to be even because we're going to end on them. So they're actually going to be odd. And in that particular situation, all we have to do is check if everything else, first off, is everything else even? Well, if you check all your vertices, you have degree 2, degree 4, 2, 4, 2, 2, 2, 2, 2. So everything's good. We do the same thing where we start at A and we're like, all right, I'm just going to make a trail as long as I possibly can. So I come over here to H. And then I can go to F, to E, and I can add on a circuit. That's the funny part is I can still add on circuits here, and then I can go to or, but I could have, there's a lot of different ways. I could have then gone I and back to E. So we're passing through H and E a lot of times, but then from there, I'm just going to move the rest of the way through the house. So there is actually a circuit and it's really, really cumbersome, but I mean, not a circuit, but a trail. And that's the only value really we have of these sort of things. Can we traverse in a specific direction? We allow ourselves to come back and pass through. Well, that's useful if I'm doing, for instance, trying to travel around a town where these are hubs. These are each different. I'm going to start here and I want to end here. And I want to hit each and every single location. Can I do it without using the same road twice? Where if these are locations or intersections I'm passing through, can I do without using the same road twice? So we can tack this from a lot of different concepts like this. All right, I mentioned that Hamiltonian concept, and this is kind of a very valuable question. So Hamiltonian is again based on the mathematician Hamilton, not the play. And he introduced an idea called the dodecahedron. And part of this question is based on that, and part of it's just a very interesting question in general. Hamilton asked a question, and this, if each vertex is labeled with the name of a city, London, Paris, and so forth, he asked, can you start at one city and tour the entire world by visiting each city exactly once and returning to the starting city? So now that means that we're not hitting any vertex twice. And that is what makes this challenge. So one way we do that, so we have this fancy shape right here, which is 3D, but if you, so to speak, open it up, you get this shape right here. Now, if I do this, the question is, can I hit every single vertex and get myself back? And as you can see right here, you can. It's a little bit trickier to see actually how he came up with that idea. And Hamiltonian, it turns out, is actually much harder than Eulerian. Eulerian was about edges. Hamiltonian is about vertices. So Eulerian I just didn't want any repeated edges. Hamiltonian, no repeated vertices. Don't know how to tell you the H and the V, how those correspond, but the E's correspond very clearly. That's the way that I would memorize that one. So graph is Hamiltonian if there exists a cycle that hits every single vertex. So you don't have repeated vertices except for the beginning and end, and you do not have anything else. Now we have a couple things that we do know. This is if a graph is Hamiltonian, then G has a subgraph H with the following things. H contains every vertex of G. H is connected, and H has the same number of edges as vertices, and every vertex of H has degree 2. All right, what do I mean by that? And this is actually really, really hard. Notice it says that if a graph is Hamiltonian, then all these things are true. So if any one of these things are not true, so if we try to pick a subgraph, and you might as well just draw a cycle, by the way. This descriptor is making it just as hard as actually the problem is. So if I'm here, for instance, I'm asking, is this Hamiltonian? The answer real quickly is no. And it's quite simply because of B. There's no way to get from A and E over to C and back with going through B only once. Because I have a vertex right here in the middle, which by the way, this is called a cut vertex, because if I delete it, they're disconnected. Then it's impossible to have a Hamiltonian cycle. And in that particular situation, we kind of can't work our way through it. So it doesn't matter what you pick because everything you pick is going to have to cross through B twice. So they want to talk about all these different things. Let's propose the 5 connected vertices and show that those don't work. Well, the edge AB cannot be removed because if it were, then A would have degree less than 2, which doesn't. So it's just saying, if let's just look about taking away edges. If I take away this edge, well, this gets too small. I'll take away this edge, this gets too small. So I can't take away any edges, but since I can't take away any edges, I have to pass through B multiple times, and that's the problem that we have. So Hamiltonian, again, is about trying to draw a cycle. And it's the very concept that's the basis of the traveling salesman problem. So those who don't know, the traveling salesman problem is imagine that you have a map with 4 cities and the distance of kilometers between them. It doesn't be kilometers, it could be miles. It doesn't, it's just a distance. It's really a cost. We're doing distance. But the salesman wants to travel to each city exactly once, starting at A and ending at A. Which route will minimize the total distance that will be traveled? So there's a lot of different paths that obviously can be done. You can go A to C to D to B to A, D, B, A. I could have gone, and so we can kind of sit here and kind of work through all these different problems. And if we do that, we have really 3 different options that go around A, B, C, D, A, B, C, D, A. I have A, B, D, A, B, D, C, A. The other one's A, C, B, D, A. So there's 3 different options I can have, and everything else is just, well, the same sequence in a different order. The problem with this, by the way, and then we can compare and see which one's the best. Well, this first one going around the outside turns out to be the minimum. Here's the problem about the traveling salesman problem. To directly do it using all of this is actually an NP complete problem, meaning it is computationally complex on a very large graph. It's really, really hard. It's not a polynomial solution to this thing. However, we can approximate it in polynomial time very, very quickly. And so those of you who will take your algorithms class, this is a classic problem we look at because there's ways to approximate the answer. It doesn't actually give you the answer. It just approximates it and it gets close enough that we really say it's good. And that is the only reason why we love the traveling salesman problem is because it's an idea. Now, Hamiltonian in general is very, very still open. Truthfully, there's no just hard and fast rule about even powers, that whole idea. You could try to come back and say, like they said, can I remove edges and how's that affect? Once I give you a much larger graph, that all goes out the window and becomes something that's a little bit harder to see and understand. Good luck, and let me know what questions you have.